it's time to take a look at how the ideal gas law can relate to density. So we know that PV equals nRT. We also know by this point that PV is equal to mass over molecular weight, RT. The definition of density is mass divided by volume. So in this little formula that I just wrote over here, do you see mass and volume? That's right here. Oops. I was going to use a different color, but I haven't used this pen for a while. So I guess I won't. I won't use that color. I'll use this color. Oh, here we go. So here's your mass, and here's your volume. So if I could rearrange this equation to get mass on top and volume on the bottom, I would have density. So let's do that. Using your algebra skills, how do we get rid of the molecular weight? How do we, what I called in a previous video, clearing the denominator? So we're going to multiply both sides by molecular weight. Molecular weight cancels, and now I have molecular weight, P, I'm going to put parentheses so I can keep all the variables separated, V equals mRT. And then, if we divide both sides by RT, now, the reason I'm doing that is I'm trying to get mass on top and I want volume on the bottom. In just a moment we'll do that. So now I have RT canceled, so I have this formula, molecular weight, PV equals mass, and then that is divided by RT because it didn't cancel over here. So now I'm going to divide both sides by volume, because if I divide by volume, that clears the volume off of the left side and puts it over here. Remember that you can do the same thing to both sides of the equation, and the equation is still true. So volume cancels. So now I have molecular weight times pressure divided by RT equals mass over volume, but that we see up here is equal to density. Okay, so that's our equation for density, molecular weight times pressure. So density is equal to molecular weight times pressure divided by RT. I'm going to rearrange my sophisticated whiteboard and come back to this problem. So now we want to find the density, and we want it in grams per liter. So we know it's krypton. So to find out, you got to find the mass of krypton. And krypton's over here. It looks like it's 83.8. So if we go back to our camera, 83.8 is a molecular weight. The pressure is 671 millimeters of mercury. Now remember, the R value that we've been using is the 0.0821. That's in liter atmospheres per mole Kelvin. This was in grams per mole. I should write that unit in there. All right, the pressure, then we had to change from millimeters of mercury to atmospheres. So let's do that out on the side. 671 millimeters of mercury. Millimeters of mercury here, atmospheres here. 1 is 760. So then we come to our calculator. 671 divided by 760 0.88 atmospheres. I'll call it 0.883 atmospheres. Okay, the temperature has to be in Kelvin, and the temperature is 47 C, so 273 added to the 47 is 320. All right, so K's cancel. And if you look and see what doesn't, let's see what else cancels. Atmospheres would cancel from here to here. This is moles on the bottom and moles on the bottom, so if I flip this and multiply, moles will cancel. Grams and liters don't have anything to cancel with. So the math is 83.8 times 0.883 divided by 0.0821 divided by 320, 2.82. And that would be grams per liter. I'm just going to double check and make sure I didn't watch my keys, so I'm making sure I did it right. 83.8 times 0.883, then divide by 0.0821, and divide again by 320. Got the same answer twice, so it must be correct. So that would be the gas density. So density is just another variation on the ideal gas law formula when you're working with the density of gases.